v equal to 3x plus 4y plus 5z, for example. So 3x is x in x direction, so it's a basis. Y is in the another direction, so it's a basis in vector space. Similarly, in quantum mechanics, we call this as in Gilbert space. We'll deal Gilbert space later. So capital Psi represents a system which consists of small particles. Each particle is represented in terms of basis. Okay, they are linearly independent vectors. One cannot be written in terms of another one. So linearly independent vectors, which we studied already in mathematical physics. So if you are so good at mathematics, quantum mechanics is very simple. So this is the idea. So capital Psi equal to A1 Psi 1, which is the basis for the first particle, plus A2 Psi 2 plus A3 Psi 6. They are all linear combination of all the wave functions. Linear combination of all the wave functions. Linear means the transformation from one state to another state will be linear. The transformation. For example, if 3 chairs are here, so I am going to tell you anyone to occupy the chair. You will occupy any one of the chair, correct? Suppose if electron is there, electron will occupy all the chairs, linear combination of all the chairs, because electron is considered as a wave. We are considered as a particle, big particle. Okay, electron considered as a wave. So electron will occupy linear combination of all the 3 chairs. We are going to measure the electron where it is. Then electron will transform from one state to one chair to another chair. Okay, then it will go into one chair. It will occupy only one chair. This transformation is nothing but linear transformation. So linear transformation. Okay, so psi equal to A1 psi 1 plus A2 psi 2 plus A3 psi 6. So 3 basis states suppose we consider. Then we are going to find out psi star psi. Psi star psi means you are going to take the complex conjugate of all those things. Psi star. So this is a normal vector. Correct. So now you will have to multiply these two. Correct. You will have to multiply these two. So A1 star psi 1 star multiplied by A1 psi 1. You pull A1 squared out. So psi 1 star psi 1. Similarly, you multiply this and this. You pull A2 mod A2 squared out. You multiply these two and you pull A3 mod A3 squared out. So this will give you answer as 1. Very good. This will answer as 1. This will give you answer as 1. I have not written the other combinations. Why? I have written only 3 combinations. I can also write this combination. Correct. This combination. I can write this combination. I can write this combination. I have not written other combination. Other combinations will give you answer 0. So that's why we have not written other combination. Okay. So now you pull, this answer is 1, 1, 1. So this will give you the answer. Mod A1 square plus mod A2 square plus mod A3 square. Just now we discussed this is normalized, so which is equal to 1. It implies that this is equal to 1. So it implies that the sum of the squares of the amplitude is equal to 1. So very important. Sum of the squares of the amplitude of all the small particles will give you always 1. Okay. If 2 wave functions are normalized and orthogonal, then these wave functions are said to be orthonormal wave functions. Then the wave function is complete. If the wave function is complete, that means wave function must be normalized as well orthonormal. Okay. If the wave function is orthonormal, then in quantum mechanics we see that it is complete. That's a technical word. Now the last one, this is expectation values. The expectation values. So far we discussed about wave function. Wave function is related with the probability. Correct? Probability amplitude. Whenever we talk about the probability, we always think about probability distribution of particles. Correct? Probability distribution of particles. We always think about probability distribution must be there. Collection of particles will be there. We will have to take the average value. We will have to take the most probable velocity or most probable speed of the particles, which we studied earlier. So most probable. So for that we need to have some expectation values, mean values, average values. So average value of the probability distribution. So the expectation value is denoted by this symbol. So you have a new symbol. This symbol denotes like this. This means this is expectation value, mean value. So there will be a number of particles. We are going to take the average value, expectation value. And any operator, all the observables are associated with the operators. All in quantum mechanics, observables. For example, in classical physics, we are going to take the readings. They are all observable quantities. Similarly, in quantum mechanics also, those readings are called observables. All observables are associated with the operators. What is the meaning of operator here? In mathematics, what will do operator? Operator is nothing but differentiation is an operator. D by dx is an operator. Integration is an operator. Squaring is an operator. Minus, subtraction is also operator. So everything is an operator. Okay, in mathematical term, we can say operation is nothing but squaring. Okay, multiplication, adding. So they are all operators. So average value, the definition for expectation value, definition for average value is taken as, you have the operator. This cap denotes it's an operator. This is the expectation value. So a letter with a cap will give you letter with a cap will give you operator. So it means F is an operator. F is an observable quantity. F is an operator. F is an observable quantity. Okay, which is sandwiched between complex wave function and its normal wave function. I repeat. So this is expression value. This expression value is nothing but operator sandwiched between complex wave function and the normal wave function. So this is the way that we are going to write the expectation value. So F is an operator. Provided this is normalized. Okay, suppose if it is not normalized, we are going to see. We will multiply by a suitable normalization constant. That's all. So now we write the same thing. We have written the same thing. Now this operator operates on the wave function. This operator operates on the wave function will give you eigenvalue with the wave function. Come on, for example, say just take this is operator. Just now I said differentiation is an operator, correct? So d by dx, x squared is, for example, x squared is a wave function. We just consider this x squared is a wave function. So we are going to differentiate. Answer is 2x. 2 is the eigenvalue. X is a wave function. Another wave function. Is it clear? This is called eigenvalue equation. This is known as eigenvalue equation. So you have an operator operates on the wave function will give you eigenvalue with the wave function. Suppose if wave function, both the wave functions are the same. For example, d by dx of e power x. Answer will be e power x. What is eigenvalue? 1. 1 into e power x. So eigenvalue is 1. Correct? So if both the wave functions are the same, we say this is eigenfunction. If the wave functions are different, we can say simply that it's a wave function. Is it clear? If wave functions are the same, we can say this is eigenfunction. This is eigenvalue. Operator operates on the wave function will give you eigenvalue with a wave function. So operator operates on the wave function will give you eigenvalue. Now it's a eigenvalue. See, look at this top. There's a cap. Here there is no cap because it has become a value number. I can pull this number out. I can pull the number out. I can write as it is like this. Correct? What is the value here? If it is normalized, answer is 1. So F is nothing but eigenvalue. I have started from expectation value. So expectation value is nothing but the eigenvalue of the operator. So expectation value is nothing but the eigenvalue of the operator. Is it clear? Expectation value. We will see more examples. So V is the potential energy, it's an operator. Kinetic energy is an operator. Total energy is an operator. Okay, in quantum mechanics, all these functions are dynamical variables. Dynamical variables are associated with the position and momentum. If any variable which is related to the position and momentum, they are all called variables. all variables are observables. All observables are associated with the operators. Clear? So operators are indirectly are associated with the position and momentum. You have a variable which is related with the position and momentum, it is an operator. Is it clear? It is an operator. So potential energy is a function of position, correct? Potential V of x, V of r. So it's an operator. So operator, expectation value of operator can be written as like this, correct? The expectation value of the operator can be written like this. So V operator sandwiched between wave function and its complex conjugate. Similarly, anything, suppose we consider A is an operator, okay, the expectation value can be written as like this. So far we have seen only normalized wave functions. Suppose if it is not normalized, then the formula is like this. So suppose this is not normalized, then we can say that this expectation value is nothing but ordinary one divided by normalization constant. Okay. Thus the expectation value is the mathematical expectation for the result of a single measurement or its average of the large number of measurements for an independent system. As I said earlier, psi1, psi2, psi3 are all linearly independent vectors, correct? Can you remember? So one cannot be written in terms of another one. X cannot be written in terms of y cannot be written in terms of z. So they are all linearly independent vectors. So this will work out only for the linear independent. So independent basis. Okay. So they are all independent systems. The total energy, for example, if you have total energy is a sum of kinetic energy and potential energy. So this is the expression for kinetic energy. This is the expression for potential energy. Just take the average value, expectation value. So this is simple as I said just now. So this is symbol for expectation value in quantum mechanics. So the expectation value of total energy is equal, is a sum of the expectation value of the kinetic energy and the expectation value of the potential energy. Now we are going to introduce the operator. E operator in quantum mechanics defined as H cross partial d by dt. Okay, E operator, probably which you have studied earlier in third year UG. So E operator, which is a cap, okay, like this. E operator is defined as H cross partial d by dt. Similarly, P operator, momentum operator, is defined as minus H cross del partial d by dx. This is d by dt. So it's an operator, E operator. This is a P operator. H cross equal to H divided by 2 pi. So it is reduced Planck constant. H bar is nothing but H cross or H bar, doesn't matter. Somebody will say H cut, okay, doesn't matter. But H cross equal to H divided by 2 pi is a reduced Planck constant where the value of H is 6.626 10 power minus 34 Js. Is it okay? So now we are going to write this equation in terms of operators. Okay, in terms of operators. So we know already E can be written as H cross d by dt. Finished, easy. Whereas now P squared exists. Here it is P. So we will have to multiply with the P operator. Okay. P dot P, which is equal to minus H cross del dot minus H cross del. Of course, minus plus will give you plus I into I squared minus 1. So minus H bar squared del squared. The second term becomes minus H bar squared del squared divided by 2m. Correct? Plus multiply throughout by psi will give you this one. This is nothing but the Schrödinger wave equation, which we are going to see in the next class. Okay, this is nothing but Schrödinger wave equation. Conservation of energy. So Schrödinger has taken this concept, conservation of energy and the wave function. The solution of this will give you wave function psi. As I said earlier, can you remember F equal to ma, m into d squared x by dt squared. The solution will give you x position. Similarly, this Schrödinger wave equation, the solution of Schrödinger wave equation will give you psi. Psi is very important. Okay. So now you are going to multiply on both sides by psi star. So this will give you psi star IH cross d psi by dt. Correct. So psi star multiplied by psi star d psi. What is this one? Simply we can say that this is an operator sandwiched between complex conjugate and the normal one. What is that one? Which is nothing but the expectation value. Correct? Simple one. Similarly, you can go for another one. We have the kinetic energy operator sandwiched between normal and complex conjugate. That will give you the expectation value. So this is nothing but the expectation value of the total energy. So expression of the total energy is nothing but sum of average value of kinetic energy and average value of the potential energy. So this is the equation 1.23. So far we started with the wave function, correct? Just to recall whatever we have discussed. We started with the wave function. We have introduced the wave function, which is the basic concept in quantum mechanics. All quantum particles are represented in terms of wave function, any wave function. Then we discussed the normalization, orthogonal, orthonormal wave function, correct? Then after that, the expectation value. So how you are going, that very important thing is physical significance of wave function, the 5 points. So those points are very important. How you are going to interpret the wave function. So this question may come under section B. So now we are going to discuss 3 problems. 3 problems are very important problems. Any one of the problems may occur in question paper. Okay. Find the normalization constant of capital psi equals psi 1 plus 2i psi 2. Okay. So we are going to find out the normalization constant for this wave function psi 1 plus 2i psi 2. We know already this formula, correct? Can you remember? Mod a1 square plus mod a2 square plus mod a3 squared equals 1 already, we know already. If there are 3 bases, here we have only 2 bases. So immediately you can find out that. So what is the probability amplitude? 1. What is the probability amplitude? 2i. So 1 square plus 2i square, mod 1 square plus mod 2i square. So which is nothing but 1 plus 4 is equal to 5. Correct? So the answer will be 1 by root 5. So square, that side you will go 1 divided by, this is square. So 1 divided by root 5, that will give you psi 1 plus 2i psi 2. So this is a normalized wave function. A, your a squared will be 5, correct? 5 a squared will be 1. So a squared equal to 1 by 5. So a equal to 1 by root 5. Don't forget. 5 a squared equals 1. 5 a squared equals 1. Okay. So your a squared will be 1 by 5. So a equal to 1 by root 5. So normalized wave function. This is normalized wave function. 1 by root 5 is normalization constant. So the new wave function, this is the old wave function. The new wave function will be psi 1 divided by root 5. For psi 2, 2i divided by root 5. This is not normalized. This is normalized. Is it clear the difference between these two? This is not normalized. After the normalization, the new wave function becomes 1 by root 5 psi 1 plus 2i psi 2. So individually you can write like this. So this is not normalized. This is normalized. This is not normalized. This is normalized of the second wave. So is it okay? So we know already for the 2 bases we can write psi equal to a psi 1 plus b psi 2. Then normalization constant can be written as this formula. Okay. Now we will go for the second problem. Normalized wave function psi of x equal to n e power minus alpha x squared, where n and a are constants over the domain. And of course x lies between minus infinity and plus infinity. So we know already normalization constant n squared psi star psi dx equals 1. We know already this formula, correct? So n is there. Earlier a was there, correct? Now n is there. Doesn't matter. N or a doesn't matter. They are a normalization constant. It can be b or it can be c, anything. It's a normalization constant. So n squared psi star psi dx equals 1. What is the value? It's given as n e power minus alpha x squared, correct? So n squared, the complex conjugate of this one will be this one. The ordinary wave function will be this one. Multiplying these two, that will give you e power minus 2a x squared dx. So which is equal to 1. Okay. Now the standard integral, the answer for the standard integral is root pi by 2a. So it becomes n squared, you have to instance, so that will give you root pi by 2a, which is equal to 1. So n squared will be this one. So n equal to 2a by pi. Already you have to the power 1 by 2. So it becomes 1 by 4. So the wave function becomes, this wave function becomes with the normalization constant 2a by pi to the power 1 by 4 e power minus ax squared. So this is not normalized, this is normalized wave function. So we have normalized. So okay, any doubt in the problem 2? So now we will go for the problem 3. So a particle constrained to move along x-axis in the domain x lies between 0 and 1. Okay, so you have 0, here L is there, the particle moves between 0 and L. So this is one dimensional problem, we will say always. As a wave function, it has a wave function n sin n pi x by L, where n is an integer. Now we are going to normalize one. Second one, we are going to evaluate the expectation value. So we are going to normalize and we are going to find out the expectation value. So normalization is very simple, that we know already. N squared psi star psi dx equals 1. So instead of that, we just substitute this, okay, this wave function. So that will give you sin squared n pi x by L. We know already sin squared x equal to 1 minus cos 2x. So substitute the formula, 1 minus cos 2n pi x by L. So separately you can integrate. You can integrate separately, that will give you n squared dx minus this second term. Okay, very simple. So when you are going to integrate dx, that will give you x. Using the limit 0 to L, that will give you n squared L. It's a very simple one. And second one, we have already integrated. Okay, we have integrated cos 2n pi x by L divided by 2n pi by L. So that will go up, that will give you L divided by 2n pi, sin cos becomes sin, so you have 2n pi x by L. Now you substitute the upper limit. So L, okay, you have to substitute for x, correct? So L gets cancelled. Now you have sin 2n pi by L. Sin n pi always will be 0. Okay, sin pi, sin 2 pi, sin 3 pi, sin 4 pi, sin n pi becomes 0. So second term will be 0. You have the first term alone. So you have n squared L minus 0, which is equal to 1. So n equals root of 2 by m. So you have to substitute now with the normalization condition. So your psi of x equals root 2 by L sin n pi x. So normalized wave function, not normalized wave function. So we have found out the wave function which has been normalized now. Now we will have to go for the expectation value. So expectation value of the momentum. So it is asked expectation value of the momentum. What is the expression for expression with the momentum? Momentum is an operator, correct? So it moves p of px, it means in the single direction, okay, px. So p is sandwiched between psi star and psi, correct? So you can write p, instead of p you can write in terms of operator, minus ih cross partial d by dx, correct? We have already studied. So instead of psi star you write here, instead of psi you write the wave function, expression for wave function. Now you pull minus ih cross out because it's constant. So you can pull, we have pulled out. So 2 has been pulled, your minus has been pulled, I is there, 2h cross divided by L out of integration constant as constants. So remaining term, you can write the remaining term. Now you will have to differentiate with respect to x only once, correct? Second term should be differentiated with respect to x. So when you differentiate with respect to x, that will give you cos n pi x divided by L divided by n pi x by L. So there's a mistake it seems, correct? No. So you have to differentiate. So we have differentiated now. Instead of differentiating, we can write in a simple way. Come on. 2, just to pull these two inside. 2 sin n pi x by L cos n pi x L will give you sin 2 theta. So sin 2 theta will give you 2 sin theta cos theta. So it's a simple way. We can do it. Correct? 2 sin theta cos theta will give you sin 2 theta. Okay. So this 2 has been pulled inside. Now you have L squared minus is there, I is there, you have n pi h bar is there, correct? So put together that will give you sin 2n pi x by L. Now you are going to integrate. So now you are going to integrate. So will give you, when you integrate sin, that will give you minus cos. So minus, you have minus will go off. So I n pi h bar by L square. Okay, when you integrate this one, sin 2n pi x by L will have cos 2n pi x by L divided by 2n pi by L, that will give you L divided by 2n pi. Okay, now you will have to substitute for the limits. When you substitute for the limits, will give you cos 2n pi L by L, this L will go off, cos 2n pi, cos 2n pi, cos n pi, cos 3 pi, cos 4 pi, everything will be 1. So you have 1. Cos 0, 1. So you have 1 minus 1. So the value is 0. The expectation value of the momentum is 0. Very, very important concept. The expectation value of the momentum is 0, whereas the wave function exists. We can find out the position, okay, but we can't simultaneously we can't find out the momentum. What is this law called? Uncertainty principle. The momentum cannot be known. Momentum is not known, whereas position is known. If we know the position, we can't find out the momentum. If we know the momentum, we can't find out the position. So this is uncertainty. Uncertain. We do not know. So uncertainty. So the momentum, the expression of the momentum is 0, provided we know already the position where the particle is there. Okay. So your assignment will be, you just find out Px squared. You have to find out the average value, expression value of the momentum square. So what will you do? You just square this one. So you have to differentiate 2 times. That's all. You have to differentiate 2 times. Your answer will be pi squared h bar square divided by L square. Okay. So you will get the answer as pi squared h bar square divided by L square. So you have to differentiate 2 times. That's all. So problem 4. Consider a one-dimensional particle confined in the region. The same problem, one side. Okay, one dimension. So particle, the position of the particle x lies between 0 and L, and its wave function is governed by, so this wave function. Earlier sine alone, now sine and e power. So sine pi x by L e power I omega t. Calculate the probability of finding the particle in the interval. This is one interval, this is another interval. So we are going to find out the value of the probability of the particle, okay, in this interval as well as in this interval. So we will take this one. What is the formula? Not normalized. Okay, we do not know the normalization constant, so this is not normalized. So for this one, it gives x lies between L by 2 to 3L by 4. So L by 2 to 3L by 4. Psi square dx divided by, what is the range? Total range 0 and L. So 0 to L. 0 and L. Is it okay? Now, what is psi mod psi square, psi star, psi? So psi star, what is psi star? The same sign, you can write sign. This e power I omega t becomes e power minus I omega t, psi star. So you can write psi star as this one. So sine and this sign will be multiplied, will give you sine square. E power I omega t multiplied by e power minus I omega t will give you 1. Is it okay? Is it clear? So similarly, you can write the terms in the denominator too. So this answer is 1. This answer alone will exist. Here also this answer alone will exist. Limit will be changed. See, limits are different. Here the limits different. So sine square pi x by L divided by sine square pi x by L. If you substitute the limit, you will get 0.205 L divided by 0.5 L, 0.41. It means 41%. The probability of finding the particle between this point and this point will be 41%. Is it okay? Similarly, you can go for the last one. X lies between L by 4 and 3L by 4. The same formula, you are going to apply the same formula. Okay, so L by 4 to 3L by 4, and your square interval function divided by the normalization. Okay, so you substitute everything and you will get this expression. You substitute the upper limit and lower limit, you will get 0.409 divided L divided by 0.5 L, and you will get 0.82. So 82%. So between these two regions, the particles are found to be more. Here we have only 41%. Here we have 82%. So particles are found to be more in this region. Okay. So we will stop today. And tomorrow it's a very important class. We are going to discuss Schrödinger equation, which will come under 10 mark questions. So thank you, students. Bye.